Hello, my name is Caleb LaQuey, and I am a senior mechanical engineering student studying at LeTourneau University in Longview, Texas, here with the A&M's online research experience program for undergraduate program through Texas A&M University. The project this year that I've been assigned to is modeling kinking in layered structures, and I've been doing so in collaboration with Dr. Ankit Srivastava with Texas A&M University, Hemat Rathrod, who has been very helpful in helping me to understand the concepts and ideas involved with kink band formation. And then Umer Ben Nassim, who's been very helpful with showing me how to use the finite element analysis software ANSYS. So let's dive in. So modeling kinking in layered structures. Kinking is an obtuse mode of deformation and or instability. So this means that it's a form of uh, deformation that occurs similar to buckling. However, it occurs in different situations to buckling. It's not as well studied in different types of situations. So kinking can occur in a variety of materials and a variety of situations, ranging from layered structures, for instance, fiber composites, to a deck of cards, to metallic laminates, to different, and it can also be used in different crystalline layered structures. Kink is extensively studied in fiber composites and is explained as localized buckling in fiber composites, where each individual fiber can buckle, but they all buckle together. However, kinking can occur under different conditions in different materials. For instance, in a stack of paper, kinking occurs under axial plus lateral compression, whereas in copper niobium nanolaminates, kinking simply occurs under the actual compression without any need for lateral constraint. So the objective of our project this semester has been to develop a finite element model to simulate and analyze kinking in layered structures. To this end, we've been using the general purpose finite element analysis software known as ANSYS. So over here, you can see several different types of kink banding demonstrated. So we have kinking in a stack of papers, kink bands being formed in carbon niobium nanolaminates, and then also kinking taking place in a deck of cards with the different compressive forces demonstrated there. So for instance, kinking occurs in a stack of papers under both axial and lateral compression. Kinking occurs in fibrous materials as the individual fibers bend and eventually bend together. So one of the things to note with this is that kinking often occurs in composite materials, as the fibrous material in the composite kinks because it is constrained, because it cannot buckle due to the constraints of the surrounding material in the composite. In carbon niobium nanolaminates, kinking simply occurs under the axial compression without any lateral constraint. Now, this is due to the specific friction between the layers, because the friction between the layers of carbon and niobium is high enough that it holds them together without delaminating naturally. Kinking can also be observed naturally. So for instance, here we have kinking occurring in spruce wood as it does so instead of just buckling naturally. So kinking is modeled differently based on the type of material being modeled. So in plastic crystalline structure, kink banding occurs due to compression and rotation of the crystalline lattice. Yet in fibrous materials, kink banding can occur as the material compresses and then it will stretch and rotate. So you have this demonstrated on either side here. Here we have a plastic crystalline structure, compresses and then rotates. And then over here we have a fibrous material where in the three different stages of that, where the material is compressed, but then not only does it rotate, it then stretches once again. In all cases, kink banding occurs as the material rotates to relieve compressive stresses, and it does so instead of buckling, which is primarily the alternative to kinking. So simple demonstration using a deck of cards. So many of the principles used in kink band formation can be demonstrated using a deck of cards. So here we have a deck of cards, and they have been able to, you're able to simulate this or to perform experiments on this in the real world. So for instance, you have the compressive forces here. As the cards compress, they buckle. And then the other thing that they do is they delaminate, the layers separate. However, you can model this using your hands and maybe some C-clamps or other materials to develop it where you can understand how the material will rotate, and then form a kink band, as sort of seen here as you see the bending in the deck of cards. So how are we going to simulate kink banding? So we're going to use ANSYS. In doing this, we had to do multiple different attempts. We used a explicit dynamic model, which was responsible for some delamination between layers in certain simulations that we ran. The material was constrained with a -0.1 meter per second velocity and a fixed support. Those were the boundary conditions used. And then multiple layers are, the reason why we chose to do this was because it was use copper and niobium, was because multiple layers of copper and niobium are simple to model rather than over constraining the system by adding in constraints, lateral force constraints or lateral fixed structural constraints. In order to determine where kink banding began and buckling ended, we took note to the decrease in reaction force as a function of displacement shown over here. So you can see when the material was compressed by 0.02 millimeters, buckling occurred and the stresses were relieved. So once this sort of hump here disappeared, we knew that we were observing kinking rather than buckling. So we started with single layer simulations. So this we did to develop, we could develop the 2D model and learn how to use ANSYS. So over here we also use boundary conditions of a fixed support on the bottom, constant velocity on the top for 1 second to give us a 10% strain. Here we have one copper layer here, and you can observe the elastic region and then the plastic deformation taking place here as material buckles. And then here we have niobium, which in this region remains elastic as it is put under compressive stresses. So then we moved on to simulating multiple layers. So for instance, here we have 2 layers of both copper and niobium taking place and both buckling together. And then we increased that number of layers to 4 layers once again. So you can see the increased niobium causes the material the buckling to occur at a higher required force. Simpler models were used to develop the skills and to determine what a larger model would be expected to look like. As the number of layers increases, this increased the friction between layers, making the buckling more difficult. So this was already described as the main mechanic that prevents buckling once you get to a certain amount of layers. Now, additionally, once we did this, we would just keep on adding and adding and adding layers. And so we were informed that this would definitely take too much time. So we moved on to doing larger 60-layer simulations. So we moved on to 60-layer simulations. So the specification of the simulation is that the model is 1 meter by 0.5 meter by 1 millimeter thick. The idea is that this is unit value so that the results can be scaled. Each layer is 1/60th the width, so that winds up being 0.08333 meters. And the mesh that we used was the width of each individual layer of copper and niobium. So once we ran the simulation, you can observe as it approaches the increased strain, about 15 to 20% here, you can observe the formation of kink bands. And what's remarkable about this is that this is very similar to what is observed in nature, shown over here. So what caused our simulation of kink banding to be successful? Well, kink bandings form when in materials that are anisotropic, with one length that's significantly longer than the other. So in our case, each layer was 1 meter by 0.008333 meters, have dissimilar strengths. So this also contributed to this because copper is a much softer material than niobium. Uh, so that gave the material sort of the space it needed to kink, and then are allowed to move against each other, but are naturally prevented from delaminating. So it's not so much that the materials are constrained directly against each other, but they're allowed to slide up and down against each other, and those conditions enable kinking. Here you're able to see the force reaction versus displacement graph and how that continues. So we're definitely not observing buckling, but then towards the end, when the kink band forms, uh, towards the end of when the strain rate gets high enough, the compressive stresses are relieved. So what are the conclusions from this? Kink bands are formed when layered materials are compressed due to the friction between the individual layers constraining the material to prevent buckling. So this was an example of one of our previous attempts at forming kink bands here at a 10% strain rate. We also discovered how playing cards can be used as an effective tool for demonstrating the concepts involved in kink band formation. Kink banding is also able to be modeled using copper niobium layers because they are anisotropic, have dissimilar strengths, and are allowed to move against each other, but are prevented from delaminating. And the friction between the layers is strong enough to contain the structure without having to use too many boundary conditions. So recommendations for future work. Future work should seek to increase the number of copper niobium layers used, double the number of mesh nodes to develop a more accurate mesh, and or solve the system using a static structural method rather than using an explicit dynamic method in order to achieve a clearer kink banding and more precise results. Additionally, determining the number of layers required to transition from buckling to kinking can also be researched further. So we knew that the material would begin to kink between 50 to 60 layers. So we went with the higher end of that so that way we could guarantee a result. Uh, but the exact number, that exact point at which kink banding would occur, is not necessarily known. So just like to take a moment to very much thank A&M's OREU program for their support and in working on this project. Um, and thank you very much. And we'd be happy to answer any questions which you might have from this presentation. Thank you.